So here's the data that we're going to be using. It's the same data I used in the first regression video using R. It's some cross-section data. It's taken from an example in the book by Green on econometric analysis. And we're going to estimate an equation, run a regression with average expenditure as our dependent variable, and age, own rent, which as you can see is a dummy variable, income, and also income squared as the dependent variables. Now, the first thing I need to do is to subset the data, because Green only uses observation periods where average expenditure is greater than 0. And as you can see, there are some periods here, some observation periods when average expenditure is 0, so I want to exclude those. Now, we did this in R using a command. Here in Excel, we can use the filter option. So what I'm going to do is I'm going to filter on the data, and in order to exclude these particular values here, these particular observation periods. So to do that, I need to highlight all the data here. So I'm going to drag across the column headings. I'll then go to, under the Home ribbon here, Sort and Filter, and put on the filters. That's added these filter buttons. I can then go to average expenditure here, click the drop down, deselect them all to begin with, and then simply select those where average expenditure is 0, like that. Now I can delete these by simply highlighting all the rows, which of course means just dragging down here on the row numbers. If I then right-click on any of these numbers here, I can choose Delete Row, and that's removed those those observations. Now I'll go back to Average Expenditure button, Filter button here, and clear the filter. And so I now have my subset data set. There was 100 observations before, now there's only 72, as you'll see if we scroll down here. As you can see, remember the first row, of course, is the heading, so 72 here. Okay, now, in fact, I'm going to remove these filter buttons now. I don't need them. You could leave them, but I'm just going to remove them again. I'll just highlight the rows, the columns rather. Go here to Select and Filter and just turn the filter off. Okay, so that is now my data subsetted. So this is the data set I'm going to use. Now, in order to do the multiple regression here in Excel, you need to use the regression facility, which is as part of the what's called the Analysis Toolpack add-in. Now, you may find that this add-in is already loaded. If so, you'll find it under Data menu here, Data ribbon. So if I go to Data, as you can see, there's a option here, a menu option, Data Analysis, which means I've already got it loaded here. If you haven't, then you'll need to load this Analysis Toolpack add-in. Now, to load that up, you go to the Insert menu here, where it says My Add-ins. Click on the down arrow and choose Manage Other Add-ins. You can then, where it says Manage Excel Add-ins, click Go, and then check this here and click OK. Note, as you see, because I already had it, as you saw, I already had the add-in, this is already ticked here. But if it's not, of course, you'll need to click that to put the check mark in, click OK. That will load it up, and then you'll find it under the data ribbon, data set of options as I showed previously. So I'll just cancel in this case, because I've already got it. Okay, so if I go to the data set of ribbon here, as it's called, and choose Data Analysis, it brings up the data analysis options. The one I want is regression. As you see, there's a various range of statistical procedures. I want regression. So select that, as I've done here, click OK. You get the standard dialog box here, where you can input the Y range, i.e. the dependent variable, the X range, the independent variables. Set a constant to 0 if you want, normally you wouldn't. Choose where you want the results of the regression analysis to appear, either on the same sheet or on a different sheet. Select whether you want the residuals and so on. Now, in order to do this, in order to put the X range in, the dependent variables, they have to be in adjacent columns. You can't select non-adjacent columns as you normally can using the control button. That won't work here, so I'm going to cancel out of this because I do need to rearrange the columns. So I want my dependent variables, age, own rent, income, and notice I need to create income squared as well, adjacent to each other, which you see is not quite the case at the moment. So I need to reorder the columns. Now the way you can do this is by, I'm going to move the average expenditure over here so that age, income and own rate are to get next to each other. So I'm going to select the column by clicking in the letter at the top, of course, to select the column. You then go to the border. Notice how the cursor changes to a narrower cross. Now using the right mouse button, you hold down the right mouse button, drag the column over here, and then let go and choose Shift Right and move. And as you can see, that has shifted these other columns to the right and moved our expenditure here. So now I've got age, income and own rent. Let me just widen that column a little bit, next to each other. So I'm almost there. But of course I still need income squared. That was one of the variables. So I need to create another variable here, another column in other words. So I'm going to right click here and choose Insert, which of course will put another column in to the left, which I can now call income squared. And just widen it a little bit. Okay, now of course I can simply create this by putting in a formula for this first one and copying down for the rest. So equals income. Power operator, of course, is the little inverted V here above the number 6 on your keyboard, squared. So that will square the first one. Then I can drag down here to do the rest. There are various ways you can copy the formula down, but I tend to prefer this method of simply dragging down. There we go, and that's now created my income squared column. And of course, all the independent variables here are adjacent, so that's fine. So now I'm ready to do run the regression. So let's go back to data analysis, regression. Okay, so let me put in the Y range, the dependent variable. Now again, of course, you could type in the range here or simply drag over the range on the sheet to put it in, which I'll do. So here we are, average expenditure. Of course, with a relatively small number of observations here, 72, it's fairly easy to drag down. If you had 200 or more, then it might be easier to simply type in the range. Okay, so that's my Y range. Now for the X range, which is these four here, age, income squared and own rent. So let me drag over the whole of those. So this is why they needed to be all adjacent to each other, so I can put them in one block. Like that. Okay. Right, so that's my data put in. Now we want a constant, of course. It's rare that you don't want a constant in your regression equation. You can change the confidence level for the confidence intervals from the default to 95 if you want. You'd have to tick this and then change it, but I'm going to leave that. Now I'm going to put the results on a separate sheet, which I think is better than having them on the actual data sheet. I prefer to keep the data and the results separate. So I'm going to call this sheet Model 1. That, of course, will appear on at the bottom of in the tab at the bottom of the sheet. I want the residuals to be printed out on the sheet, because, of course, we do need to check the residuals for autocorrelation, so we need to run the diagnostic tests. You can get it to plot the residuals. I actually don't do that. I prefer to plot them myself. I don't need the standard residuals or the line fit. The normal probability plot here is not particularly useful. It's not as good as the one that you get printed but in R, for example, so I'm not going to bother with that. So let me click OK. And pretty quickly, of course, we get the results here with a fairly standard printout. Now, it does, for some reason, not give proper width to the columns here, so the first thing I do is I widen these so I can read it better. So again, I just drag over the whole number of columns here, and then just double clicking any one of the borders here will extend them so that things fit better. So here we have the standard goodness of fit measures, regression statistics, the R-squared, adjust R-squared, the standard error of the equation, which is an estimate of the standard deviation of the error term of the residuals, sample size and observations. You have your ANOVA, your analysis of variance table with the F statistic, which of course tests whether there's any correlation at all between the variables. Here are the coefficient estimates with their standard errors and t-stats and p-values, and also confidence intervals. And then we have the residual output, as it's called, which in fact shows not just the residuals but the fitted values that you get, of course, from the estimated equation. And I do want both of those. Of course, they should be 72. Notice one thing, however, it's not able to guess what the names of the particular variables was. It simply calls them 1, 2, 3, 4. So it's important to immediately change that to give you the actual variable names. Now, the variables here, 1, 2, 3, 4, correspond to your, which I can see from top to bottom, correspond to the independent variables from left to right in your data set. So I'm going to copy and paste those data variable names into here. So I'll go back to my data. I'll highlight the 4 variables there. So this is variable 1, variable 2, 3, and 4. Let me right-click and choose copy. Now I want to paste this. Notice it's a row, and I'm going to paste it into a column. So what I need to do is to highlight where the variable names are going to go, right-click, so I can choose Paste Special and Transpose. So that will copy those from a row into a column. And there we are. That's copied those variable names, so now I know exactly which one they refer to. Of course, the first one is just the constant, the intercept as it's called here. So that gives me my standard result. As you can see, it's very easy to do in Excel using the built-in regression facility in the analysis tool pack. Now, before we can start looking at the t-stats and the f-stat and so on to test significance, it's important to check that the residuals, which of course are an estimate of the error term, satisfy the standard assumptions of what's called the classical model. That is, that they have a mean of 0, that they are not correlated with each other, there's no autocorrelation, and that they have a common variance, there's no heteroscedasticity. We can also check sometimes as well to see if they're normally distributed. Now, with cross-section data like we've got here, autocorrelation is not typically a problem. It's heteroscedasticity that is more likely. Now, a way to check for both of those is, of course, to look at a plot of the residuals. So I'm going to do that now. So I'm going to plot a graph here, a line graph of the residuals. So I'll highlight them. There we are, 72, of course. And then simply go to the Insert menu and choose to draw a line graph, like that. Let's make it a little bit bigger. I'll just change the title to Residuals. Try to spell it properly, of course. Okay, so there's my residual plot. Notice you can see some outliers here, one here, here, perhaps that one and that one as well, but certainly those two look like outliers, and of course you might want to remove those from the data set. Now, what about autocorrelation? Does there appear to be any particular pattern here? I would say not, but of course this is, we could run a formal test. I won't do that because I say it's not a particular problem with cross-section data typically. I'll show how to do that when in the video looking at how to run regression with time series data. Heteroscedasticity, is there any tendency for a widening variance? Well, again, excluding those two possible outliers, I think you could argue that the variance of the residuals is remaining pretty much within a fairly constant band of plus 500 to minus 500. So it's possible that there's no heteroscedasticity here. Another way to check this graphically is to plot a scatter graph of the predicted values against the residuals, which is can be used as an indication. So let me do that. I've got both things here. So I'll plot these as a scatter graph, so that means highlighting both the variables like that, first of all. And then we'll draw a scatter graph this time. Don't join up the points, of course, you want just a simple scatter graph here. Let me put this a title. Residuals against predicted. Now remember in Excel that when you plot a scatter graph, the variable which is plotted on the horizontal axis is the one in the leftmost column, in the left of the two columns here. So predicted here is going on the horizontal, residuals on the vertical. So I'm going to add a couple of axis titles now. And then change this one to predicted. It doesn't strictly matter which way around you plot these two variables here, but typically you tend to put predicted on the horizontal and residuals on the vertical, which is what I've got. So change this title now to residuals. Okay, so here we have a graph. Now again, there's those two outliers up here. So ignoring those, what do we see? Well, actually here we do seem to be getting a tendency for the variance of the residuals to be widening as we move along here to the right. So there's some potential indication here of heteroscedasticity in the residuals. And of course, if that's the case, then the t-stats and f-stats up here are not strictly valid, and we would need to either calculate robust standard errors and t-stats, which is easy to do in statistical packages, not very easy to do here in Excel. But an alternative, of course, is to try to remove the heteroscedasticity by running, for example, a weighted least squares regression. Now, just to confirm whether or not heteroscedasticity is concerned, it exists rather, then we can run, in fact, a formal test, and I'll look at how to do that now. So the the formal test I'm going to run for testing for homoscedasticity here, or testing for heteroscedasticity, I should say, is a simple, what's known as a Lagrange multiplier test. It's a fairly basic one. There are more sophisticated ones that you can run, such as the ones that I did in the R video. But this one involves simply running a regression of the squared residuals against the squared predicted values. And if the coefficient on the squared predicted values is not zero, then you have heteroscedasticity. So I've moved the graphs out of the way here so that I can then create these two variables. Firstly, the predicted values squared and the residual values squared. So let's put a formula in to do these. So equals the predicted value squared and then the residuals squared. Okay, now I've got those two formulae and I can copy them down at the same time here to do all the rest. Like that. Okay, so those are my variables. Now I need to go back to the regression facility now. So let's go back to the regression facility, which is in the analysis 2-pack, of course. Now it does remember what you did previously, so I'm going to delete those and put in the y range, which of course is residual squared. And the x range is the predicted value squared. There we go. Now I'm going to put the results of this regression on a separate sheet again. I'll just call this hetero test, testing for heteroscedasticity. We don't need the residuals of this regression, there is a constant. Everything's fine. That's all we need. So let's run the regression. Quickly get the results again. Let me widen the columns because they're always scrunched up. Okay, now this test is in fact a chi-squared test, so it's essentially a large sample test. So you do need to have a fairly large number of observations to run this. And 72 is quite reasonable, and the test statistic is actually given by nr squared. That is the number of observations times the r square value, and that has one degree of freedom. So I'm going to put the chi-squared statistic over here. The test statistic is equal to n, the number of observations, times the r squared value. Now, of course, we need to check whether that is in the tail of the distribution, or in other words, is the p-value less than 0.05, assuming a 5% significance level. Now, to calculate the p-value, you simply need to use the built-in chi-dist function. Now, notice as I start typing chi, C-H-I, of course you get the normal pop-up with suggested ones. Now, in fact, the one that I want is, well, you have a choice. You can have this one, chi-squared.dist.rt, which actually returns the right tail probability, or that's the current one, but a previous one, which is still available, is simply chi-dist. As you can see, that's available for compatibility with Excel 2007 and earlier. So you can use that one if you wish, but if you want to use the more up-to-date one, which does the same thing, It's this one here, chi.dist.rt. So we enter that. So I'm going to press the tab key to put it in, and then it opens the brackets. Notice it requires 2 bits information, x, which is the test statistic. So let me click on there to put that in, comma, degrees of freedom. As I say, it's a 1 degree of freedom test. So put in 1, close the bracket, and then press enter. And we get a p-value 0.05079. Now notice that is just slightly above 0.055%. So you could say that the null hypothesis here of homoscedasticity is not rejected. However, it's so close to being below 5% that I think it would be reasonable here to assume that there is in fact probably some heteroscedasticity. We'd expect a p-value much further away from 0.05 to be more certain that there wasn't a problem. And in fact, if you look at the video using R that I did on this, which of course is under the R fundamentals, is in the R fundamentals playlist. It's the second video on regression using R, where I run some more sophisticated tests, in particular the Broich-Pagan test and the Goldfield-Quant test. Both of those do suggest that there is heteroscedasticity. So although this fairly simple test here is not quite at the 5% level, suggesting a problem, given it's so close, then it would be reasonable to assume here that there is heteroscedasticity present. Okay, so that shows you how to run a very simple test in Excel to test for heteroscedasticity. Finally, I'll show how you can run a weighted least squares regression here in Excel to take account of the heteroscedasticity. Now, of course, to run weighted least squares, you have to decide which variable, you have to know which variable is related to the heteroscedasticity. Now, in this case, it's income, of course. And what you assume with weighted least squares is that the variance is proportional to that particular variable, either the variable itself or the square of the variable are the two most common options. If you assume that the variance is proportional to income, then you have to transform the variables by dividing through by the square root of income. If you decide that the variance is proportional to the square of income, you transform them, you weight them, in other words, by dividing through by the level of income. So looking at the first case here, I'm going to transform the variables by dividing through by the square root of income. So I've already put some labels here for these transform variables. So I've used an asterisk to indicate that they're transformed, they're weighted. And in this particular case too, you end up with an additional variable which is 1 over the square root of income. And in fact, it's the coefficient on that variable which is the intercept of the original equation that you're trying to estimate. The coefficients on the other transform variables are the same as in the original equation, but this equation has no intercept. Instead, the intercept that you're trying to estimate of the original equation, because remember we're trying to find those original parameters, but we're allowing for the heteroscedasticity at the same time. The intercept is given by the coefficient on this variable. If you're not sure of that, you'll find this explained in the in any standard econometrics or statistical text, such as Green's text. So I'm going to create these transform variables now by dividing through by the square root of income. So let's take expenditure, dividing through by the square root of income using the square root function. This one is simply 1 over the square root of income. Now we've got age. Now income itself. Income squared divided by the square root of income. And finally, own rent. So that's my transform variables, or the formulas for the first row. Now I'll copy down, of course, to do all the rest. Okay, so now I have my transform variables, my weighted variables. I can run the regression. Again, age, this variable here, of course, is the dependent variable, and these are the independent variables. But remember, there is no constant now in this equation. The constant that you're trying to estimate from the original equation is the coefficient on this particular variable here. So let's go back to the data analysis regression facility. I ran this previously, so that's why there's things in there, but so I'll delete them so you can see how to put them in. Okay, so the dependent variable is this transformed average expenditure variable, like that. The independent variables are these 5 here. Now remember, very, very important here, that you exclude the constant. And I'll put these on a sheet called, on a new worksheet, weighted least, WLS, weighted least squares 1. I'll click the residuals and click OK. And there are the results. And as you'll see, if you check, these is exactly the same results that I got in the video using R on weighted least squares. Now, remember the intercept in effect here is now the coefficient on this first variable here. So what I'm going to do is I'm going to delete this row here. I'm going to call this the intercept, because that is in fact the estimate of the intercept of the original equation. Then I'm going to copy the variable names over from here as I did before. Remember to use right-click, paste special and transpose to turn them from a row into a column. And there we have it. So those are the estimated coefficients using the weighted least squares, so that now the standard errors are correct and the t-stats should be, assuming that we were correct in our assumption about what was causing the variance, the t-stats, standard errors, now the t-stats will be valid, and it can be used, and also the f-stat and the r-squared and so on, so you can make judgments about the significance. I'll quickly plot a graph of the residuals against the predictive values I did before, which, remember, that suggested some heteroscedasticity. Let's see if it's now been removed. We could, of course, run the formal test as well. I won't do that. So let me do the quick residuals versus predictive values plot that I did before. In fact, you could probably argue that there still seems to be evidence here of non-constant variance. So it might be, in fact, that a better assumption is that the variance is proportional to the square of income rather than the level of income, in which case you would need to run another weighted least squares where you would weight the variables, that is, you divide them through by the level of income rather than the square root of income. Now, in that particular case, a constant, there will be a constant in the equation, and that constant in fact will be the coefficient on the income variable. Again, you'll need, if you're not sure on this, you need to check in your econometrics or statistical text to understand why this is the case. Okay, so I think that has made it clear how you can do quite a lot of standard regression analysis on cross-section data using Excel. It's not as easy as using some dedicated software package, but nonetheless it is possible.